In this video, we're going to once again look at how to solve database questions. We're going to review the approach and then we're going to solve the database questions for 2 years, 2017 and 2018. So this is the approach that I would usually take when doing a database question. First, I would browse through the passage. Okay, I wouldn't make an attempt to understand the passage yet. So I will just browse through the passage to get a rough impression of what each paragraph is talking about, what each table or what each figure is trying to tell us. And as you are browsing through, there will be some sentences that will appear more important than others. For example, those that communicate definitions or relations. All those sentences, I would underline it because I know that it's going to be important. Next, I will take a look at the question. From the question, there will be some keywords or guiding phrases. For example, refer to table 8.1. Okay, so based on the keywords in the question, I will go back to the respective sections and then only now would I try to digest what is that passage talking about. So I'm going to demonstrate how I use the approach to solving two database questions. Number one is the 2018 paper. So in the 2018 paper, it's talking about instrumental analysis. This is essentially related to qualitative analysis, okay, meaning we want to find out the ions present or the elements present in a mixture or in an unknown sample. Now the first part is talking about flame test. Now flame test is not really in the syllabus, okay, but if you just browse through it, it seems to be portraying that when you subject group 1 elements to hot flames, it will give off different colors. Okay, and from the colors, we can identify the group 1 elements that are present. Okay, so all I need to remember is that first paragraph is talking about flame test and each group 1 element is associated to a different color. In the next paragraph is talking about emission spectra. Okay, now emission spectra is essentially a very advanced concept or topic. In fact, if you don't take physics, the only time where we learn emission spectra or spectroscopy, which is the interaction of light with matter, is when you take chemistry in university. Okay, so but don't be intimidated by the content, just browse through. Over here, it seems to be trying to tell you that each group 1 element would give a fingerprint of lines in a spectrum. This is something like a chromatogram. Okay, so from the lines present in the spectrum, we can identify which element is present. So that's all you need to know for now. Next, we are looking at another technique called ion chromatography. Okay, so ion chromatography is like the closest that we have in the syllabus would be paper chromatography. It's used to separate mixtures in a sample. And then later on, they go on to introduce two different terms which are in bold, so meaning you need to take note, something about retention time and the height of the peak, which tells you the amount or the relative amount of each ion in the sample. Next, the question gives us two ion chromatograms, one for positive ions, the other one for negative ions. So the chromatograms are there to help us make sense of the earlier paragraph. From the chromatograms, we can see that the each peak would correspond to a particular ion. So it tells us the ions present in the mixture. This is similar to paper chromatography, where each spot tells us the components in the mixture. Secondly, the height of the peaks actually tell us the relative amounts of each ion present. So for example, in this chromatogram, we can tell that it has the most amount of sodium ions in the sample. As mentioned, there is also a chromatogram for negative ions. Now at this point, there is really no need for you to scrutinize the chromatogram or to analyze the ions present. Just need to know that there's a chromatogram of positive and negative ions. If need be, we'll come back to this part to solve certain questions. So for part A, the key phrase here would be flame test. Okay, so if you try to recall where did we read about flame test, it is in the first paragraph. So let's go back to the first paragraph and analyze it in greater detail in order to solve this question. For part A, it's asking you why is it difficult to use flame test to identify the elements, the group 1 elements. So now it is the time where we look at the table in detail. If you take a look at the table, you would find that, for example, potassium, rubidium and cesium, they have different variations of violet color. Okay, so that makes it difficult for us to distinguish between the colors. Okay, so for example, when you see a violet, how do you go on to distinguish whether it is pale violet, red violet or blue violet? Okay, between similar colors. Okay, now in your answer, it's very important for you to cite examples. So you cannot just say that it's difficult, certain elements have similar colors, therefore which makes it difficult to distinguish. You need to state very clearly from the table that potassium, rubidium, cesium have similar colors, which makes it difficult to distinguish between them. Secondly, when you have a mixture of ions, the color that you see will be a composite of all of them, so which makes it hard for you to distinguish the different colors that are present as well. For part B, you are given an emission spectrum. Okay, so that immediately your mind must be directed to the paragraph on emission spectrum, where we were given a few different spectrums showing the fingerprint lines for each element. Alright, so over here for part B, you are given a spectrum from a mixture and you are asked to identify which group 1 elements are present. So again, this is like a chromatogram. You just need to match the chromatogram of the mixture to the chromatogram of the pure samples. Okay, and the question, the database question actually gives you the chromatograms of the pure sample already. Okay, so if we take a look, we appear to have rubidium. These are the lines corresponding to rubidium. And then we appear to have also sodium. Okay, so which group 1 elements are present? You have rubidium and you have sodium. Okay, why? Because the lines that correspond to the emission spectra of rubidium and sodium can also be found in the emission spectra of the mixture. For part 2, what additional information would you need to identify all the elements in the mixture? In the earlier emission spectra, there were lines that were not accounted for. So in order to identify all the elements in the mixture, we need the emission spectra of the other group 1 elements. Okay, for example, I think cesium and francium wasn't there, and also any other elements that may be present in the mixture. So we need the emission spectra of these pure elements in order to identify what those remaining lines are, which elements are those remaining lines due to. For part C, from the question, it is obvious that we need to refer to the part on ion chromatography in order to solve this part. So the question is talking about wanting to find the concentration of sodium ions, and then you need to crystallize sodium salts from the mixture. So in order to know what sodium salts that can crystallize from water, now sodium is a cation, so it needs to combine with an anion to form a salt. And so we need to, the different salts that can be formed would depend on the anions that are present in the mixture. So therefore, we need to refer to the chromatogram which contains the negative ions or the anions. So if you look at figure 8.3, the chromatogram tells you that there are 3 different anions present: chloride, bromide, and sulfate. Therefore, the 3 different salts would be sodium chloride, sodium bromide, and sodium sulfate. So these are the 3 different salts that can be obtained from the mixture. For part 2, they give you the concentration of calcium ions, and then they require you to then find the concentration of magnesium and sodium ions. So this is the quantitative aspect of the question. And for quantitative, you need to recall that there's a part that says that the height of the peak tells you the amount of the ion present. So what do we do now is that we need to compare the relative heights of the 3 ions. We have calcium. Calcium is here, is 0.6. And then sodium is 1. And magnesium is 0.15. So by comparing the ratio of the heights of the peak, we can therefore use proportion to find the concentration of magnesium and sodium ions based on the value given for calcium. For part D, the question is saying that ion chromatograms give more information than emission spectra. Okay, give reasons to support that. So we need to go back to the part on ion chromatography, so the last few paragraphs, and find out what information can we get from it. So over here, if you look at this paragraph, they tell you that ion chromatography can allow you to identify the ions present. Okay, this we can achieve with emission spectra as well. However, there's one additional point that tells you that the height of each peak is proportional to the relative amount. So chromatography, ion chromatography can tell you the amount or the relative amounts of each ion present, which cannot be obtained with emission spectrum as well. Okay, and then there's also this last paragraph that tells you that ion chromatography can be used to identify even those that contain multiple atoms. Okay, essentially your polyatomic ions. Okay, and that cannot be done with your emission spectra. Emission spectra only works for elements. So from this part, I hope you can see that in order to answer a certain part of a question, it's very important for you to go back to the relevant paragraphs and read in detail to sift out any important information that can go into your answer. Next, we will look at the 2017 database question. Once again, I'll browse through the passage to get an idea of what each paragraph is about and also to underline the key sentences. So when we read the first part, it seems to be talking about a certain law known as the law of constant composition. Okay, what is the law about? Is this, that all samples of a particular chemical compound have the same composition by mass. And then in order to come up with the law, the scientists actually collected a few data to calculate the percentage composition by mass of different metal oxides. Table 1 gives the data of the experiment. So again, there's no need to digest the data. Definitely, if a table is given, a question will be related to it. When we encounter the question, we'll come back to the table once again. The next part of the passage talks about using chemical symbols to represent different compounds. Once again, the symbols are given. There's no need to digest them. Just know that there are symbols given for different elements and different compounds. We'll come back to it later on. So for part A, the question already tells us that we need to use the data from table 1. So I know that in a while I will need to go back to table 1 and I need to use the values in table 1 to solve certain questions. Next, the question tells us about the law of constant composition. So I know I need to go back to the paragraph on law of constant composition and I need to find out now what exactly is the law about. Okay, so the law states this, that all samples of a particular chemical compound have the same elemental composition by mass. So what does that mean is that, for example, if I have a sample of iron oxide, okay, the percentage by mass of iron is always the same as another sample of iron oxide. Okay. Similarly, if I have a certain sample of mercury oxide, the percentage by mass of mercury and oxygen, right, would always be the same as any other samples of mercury oxide. So the question now requires us to use the data in table 1 to determine whether this law applies to iron and mercury. So next we need to look at the data given in table 1. What are we given in table 1? We are given the mass of the metal. Right, we are given the mass after heating to constant mass. So what does this mean? When we heat a metal in air or in oxygen, the final mass is the mass of the metal oxide. Okay, so to determine whether iron and mercury obey the law, or whether the law applies to iron and mercury, we need to find the percentage by mass of iron in the two different samples of iron oxide to see whether the percentage by mass of iron is the same. And similarly, we need to find the percentage by mass of mercury in the two different samples of mercury oxide to find whether the percentage by mass of mercury is the same. If the percentage by mass is the same, then it obeys the law. If the percentage by mass is different, then it doesn't obey the law. So let us look at the data for iron first. In the first experiment involving iron, okay, we have 20 grams of iron, and after heating we get 28.6. So that is the mass of the total iron oxide. Now I've written the formula for iron oxide as FeOX because we don't know what is the exact formula of iron oxide. In fact, we don't really care what is the formula. It doesn't affect our answer at all. Okay. So what we need to find out now is the percentage by mass of iron in iron oxide. So that would be 20 divided by 28.6 times 100, which would give us 70%. Next, we look at the second set of data given for iron. Similarly, if we find the percentage by mass of iron, it will give us also 70%. So this shows that in different samples of iron oxide, we always have the same percentage by mass of iron, and therefore iron obeys the law of constant composition. Next, we'll look at mercury. For the first set of data given for mercury, if you calculate the percentage by mass is 92.6, and using the second set of data, it is 96.1. So that tells us that the percentage by mass of mercury actually varies from one sample to another. Therefore, the percentage by mass of mercury is different for different samples of mercury oxide, and therefore it doesn't obey the law of constant composition. In the next part, the question tells you that lead can form two different oxides, lead-2 oxide and lead-4 oxide. The question is asking you which oxide was formed when lead was heated in the experiment. So, and then they ask you to calculate the empirical formula. So when you see the word empirical formula, you need to link to what we have learned in the syllabus, that given mass data, we can actually find empirical formula. And how do we do that is by using this particular table, where we first write down the masses of the two elements or the elements present in the compound. Okay, then we divide by the atomic mass to find number of moles. Okay, so this is mass, this is number of moles, and then after that we find the mole ratio. Okay, from the mole ratio we can find the empirical formula. Now, regardless of whether you use the first set of data given for lead or the second set of data given for lead, you would be able to find that the ratio between lead and oxygen is 1:1, meaning the empirical formula for lead oxide formed in this case is PbO. So in this case, this is lead-2 oxide. Okay, lead 4 oxide actually has the formula of PbO2. So the empirical formula would be would have a ratio of lead to oxygen as 1:2 as well. For part B, you are asked to look at Dalton's formula. So I know that I need to go back to the part where the scientists actually use different symbols to represent different elements and compounds. And now we need to compare the formula for water, hydrochloric acid, and nitrogen monoxide. Okay, and see how it compares to the modern formula. So the very first thing that you need to do is to write down the modern formula for water, hydrochloric acid, and nitrogen monoxide. So water is H2O, hydrochloric acid HCl, and nitrogen monoxide is NO. Okay, so next we need to compare to the Dalton's symbol for water, hydrochloric acid, and nitrogen monoxide. So when I try to compare the two different formulas, I will compare on the basis of two things. Number one, whether it contains the same elements, whether Dalton's formula contains the same elements as the modern formula, and also the ratio. For example, in the modern formula for water, you have 2 hydrogen atoms paired with 1 oxygen atom, but in Dalton's formula, you only have 1 hydrogen paired with 1 oxygen. So for all 3 compounds, I'm going to look at the elements present, whether it matches, and the ratio of the elements, whether it is correct or not. Now in the last part, you are given the Dalton's formula for a common metal salt. This is a key word over here. You need to remember that we are looking at the salt. Okay, the formula of the salt doesn't agree with its modern formula. You are required to suggest the name of the salt, and you need to explain how do you identify the salt. Okay, now some students may attempt to analyze the elements that are present. Okay, so for example, you have, this is sodium, this is hydrogen, and this is oxygen. Okay, and then you may think that, is it sodium hydroxide or is it sodium oxide? Now, the question tells you that it is a salt. Sodium hydroxide is an alkali, it is not a salt. Sodium oxide is also an alkali, so it is not a salt. All right, so the approach of analyzing the elements is not exactly correct, but rather we need to look at, earlier we were given the formulas of different compounds as well. So the compound that this part represents, this little part actually represents hydrochloric acid. Okay, so essentially Dalton was thinking of the salt that is formed when sodium reacts with hydrochloric acid. Okay, so when a metal reacts with an acid, it forms a salt. The salt would have the cation from the metal and the anion from the acid. So the salt that we are looking at is sodium chloride. Okay, reason being, the diagram shows us that the salt is formed by combining sodium with hydrochloric acid. So when we combine sodium with hydrochloric acid, we arrive at sodium chloride.